Hello everyone, I am Anand Agrawal. I am here to present our work towards robust power grid attack protection using LightGBM with concept drift detection and retraining. This work is done in NYU Abu Dhabi with my colleague Mario Sazos, Maniatakos in collaboration with Ahmed Durra of Khalifa University. In this work, we present a robust methodology to detect cyber attacks on power grid. The existing state-of-the-art methods have certain issues, like model-based approaches lack scalability and accuracy, as it does not consider the dynamic nature of the power system, and it only classifies binary events, but does not consider natural events. Also, the machine learning-based approaches does not consider accuracy reduction over time. In this work, we have developed a realistic testbed to expose all the attack surfaces. We not only considered binary classification, but we looked into three-class and multi-level classification. And to avoid model accuracy reduction over time, we have retained our model considering the concept drift. We have used a LightGBM technique, as I mentioned before. The LightGBM technique is an Ansible-based gradient boosting machine technique, where multiple learners are trained in sequential or parallel way. The LightGBM excludes data instances with small gradients, and it converges faster and accurately. As you can see on the left side of the figure, the other boosting technique split the tree with level wise, whereas on the right side, the LightGBM technique split the trees leaf wise so that to get the maximum information gain. In our threat model, we have assumed that the attacker has access to the monitoring data and it can access the networking devices. We also considered that attacker has certain attack scenarios, like it can perform data injection to change phasor values, or it can perform remote tripping injections like closing or tripping command to the relays. Attacker can change the relay settings like changing the CT and VT ratio of the relays. To train our model, we have considered a benchmark dataset of Thomas Morris Group of University of Alabama. That setup contains 3 bus system and 4 circuit breaker. Each bus is equipped with a control circuit breaker. The dataset description is that it contains 37 different scenarios. Each scenarios consider the different phasor angle values, phasor measurement units, and attacks related to relays. It considered 3 events like no events, natural events, and attack events. The dataset contains 128 different features, which comprises of magnitude of voltage and currents. On the left hand side of the figure, you can see we have selected top 5 best performing features and lowest 5 performing features. On the right hand side of the figure, you can see the description of the feature as well as event type and scenario ID. When we have applied machine learning technique like GPM, we have considered feature set with selected features and overall set features. We found that the accuracy if model is trained with selected feature is higher than the overall set features. Like as we can see in the figure that binary classification, the accuracy increases from 96.9% to 97.3%, and in 3 class classification the accuracy increases from 95.3% to 97.1%. It shows that if model is trained with complete feature set, then there is a chances of overfitting. In our model, we have considered certain parameters like number of iteration we have run is 8,000. The maximum tree depth is 9 with number of leaf nodes as 50. The LightGPM provides a boosting type functionality to select. We have considered gradient boosting GDBT technique and gradient based one-side sampling, that is GAUSS, for generating our model, and we have also considered at the same time the concept drift. For model generation, we have divided the dataset in chunks. We have applied a massive online analysis framework to calculate the drift. We have considered drift detection method and early drift detection method to to look into the drift detection. Drift detection is uh, generally came because of the accuracy of the model reduced substantially when there is a dynamic nature of the data and the context of the data changes with time. We have retrained our model LightGBM once we find a specific point where the accuracy reduction takes place with certain limit. The model once we retrained our model, we find that the model accuracy increases in fraction. Here you can see our experimental setup schematic view. We have used RTDS hardware, which is running 9-bus simulation system developed with the help of RSCAD software. The RTDS used different types of cards like GT Sync, GTAO, GTDI, and GTNet, which is useful for getting the signals from the RTDS machine. We have implemented simulated PMUs. We have used hardware amplifier and relays for protection in overcurrent and voltage. In our setup, we have performed monitoring local as well as remote. For producing the remote monitoring connection, we have developed a VPN connection. On the remote server, we have applied and used monitoring softwares like synchrophasor protocol softwares and machine learning technique to perform data analytics. Here you can see the physical setup where you can see the gateway, the SEL switch, the local monitoring machine, the hardware relay, and the amplifier. You can also see the RTDS running the 9-bus simulation. To consider the model detection accuracy, we have used evaluation metrics. In our evaluation metrics, we have considered precision, recall, F1 score, and accuracy. We have found out that LightGBM outperformed the existing traditional machine learning approach like DNN and SVM. We found in 3-class classification, our model accuracy almost reaches to the 97%. And to avoid drift, we have dynamically retrained our model when there is a loss of 50% accuracy. This 50% loss accuracy is calculated by the previously mentioned algorithms like drift detection method and early drift detection method. Once the model is retrained by finding out the specific event sample where the accuracy degrades, then the better accuracy is achieved. In binary classification, the accuracy increases from 97.28% to 98.02%. And in 3-class classification, the accuracy increases from 96.98% to 97.73%. We have also compared our work with the related work. We have only considered the physical power system work to maintain the similarity. We have compared our LightGBM technique with other boosting techniques like ADA boost and HG boost, and we have also compared with other existing machine learning approaches. We found that LightGBM outperformed all the techniques with accuracy more than 97%. We also found that no other techniques have applied concept drift, and it is important as machine learning models, accuracy reduction takes place over time when there is a dynamic nature in the data. At last, I want to conclude that this work in progress provides 3 main insights, like providing dynamic retraining of machine learning model, focus on classifying 3 class level data so that it includes natural events, and to generalize the model for any power grid setup. In future, we will look of developing a different testing and training environment to maintain the generalism and to maintain the generalization. And we are in process of collecting more data with increased feature set. At this moment, we have not considered the feature set with timestamp, and timestamp plays an important role when it comes to synchronize the timing between the entire devices. We have also not considered the drift based on timing. At this moment, we have considered drift based on the event samples. So we will look into all these problems in future. Thank you everyone for your time.